Good afternoon. There we go. Okay, today we're going to be graphing quadratics. You might have seen this in class already, so this might be a rehash of that, but I think this will be abbreviated, so you won't have any interruptions from people with questions, anything like that. Okay, so before we graph quadratics, I want to refresh everybody's memory on how we graphed lines back in Unit 4. So every equation of a line, with the exception of vertical lines, you could put, was associated with an equation, a function, an equation, that you could put in the form y equals mx plus b. So this is a general form of any line except for vertical lines. And we called these linear functions, and we graphed them by finding x and y-intercepts. And every single one of these y equals mx plus b functions, or standard form functions, had something in common. And that was, they all had a degree of 1. The exponent for x was 1, that's why we called them, and we called these linear, the degree 1 equations. Now for the past 2 weeks, you've been factoring quadratics. We have solved equations with quadratics in them, using factoring method, using square root, using completing the square, and using quadratic formula. All of these equations will obviously not give you a line because the exponent in every case, the highest exponent, was 2. These are quadratics. Degree 2. So these graphs will not be straight lines. They will look like this or this. Later on in Algebra 2, you'll see this shape that's turned 90 degrees, either clockwise or counterclockwise. We're only going to deal with shapes that are either opening up or opening down. These are called parabolas. Every quadratic that we've been working with the past 2 weeks will give you this or this. This is called opening up, this is called opening down. And parabolas have certain characteristics. It looks like they are symmetrical, and they are. So I could draw a dotted line, a vertical dotted line through the lowest point here or the highest point here, and you would see mirror images on either side of that dotted line. So a parabola is symmetrical. And as I just mentioned, there is also a lowest point or a highest point. So there is a max or a min, depending on if it's opening up or opening down. In addition, if I were to take a parabola and put it on a coordinate system, then I have a few more important points that come into the picture. I don't only have a min here and this mirror dotted line, but now I have points that intersect the x-axis. These are, no surprise, called x-intercepts. And I have a point here where it intersects the y-axis, known as the y-intercept, of course. And if I am given the quadratic function, I am able to find these critical points, the two x-intercepts, the y-intercept. I can even find the minimum here, or if the parabola is opening down, I can find the maximum there. The min or the max actually has a more special name than that. There is one name that names either the min or the max, and it is the vertex. So whether it's a min, the lowest point on the graph, or a max, the highest point on the parabola, it is called a vertex. So the four critical points that we need to find when given a quadratic function are the vertex, which is the min or max, the y-intercept, and the x-intercept. X-intercepts, plural, if there are more than one. I say if because it is possible that your parabola doesn't intersect the x-axis at all. If I have a parabola up here and this is the lowest point, then it, of course, is not going to intersect the x-axis. And so in this case, there are no x-intercepts. I still have a y-intercept because this tail goes on forever, and this will never turn vertical. There will always be a positive slope, though the positive slope is always changing. There will always be a positive slope. So eventually, it will hit the y-axis. It is also possible that a parabola has only one x-intercept. That would happen if the vertex were right on the x-axis. So this would be the vertex as well as the only x-intercept that the parabola has. Okay, now the big question is, how do we find all these points? How do we even know where the parabola is if we're given the equation? Okay, first I'll start with how do you find the x-intercepts if you're given a quadratic? So here's an example of a quadratic. Back when we were solving, there was no y here. We had a 0 here. And a typical question would be, given this quadratic equation, solve for x. And that's when you chose whether to factor, square root, complete the square, or quadratic formula. This one happens to be factorable, so I will do that. So, okay, so my two solutions are -3 and -1. Now, graphically, think in terms of graphing. What did I just do? I made y 0. When have we done that before? Think back to when we graphed lines. We made y 0 and then we solved for x. The reason was we were looking for the x-intercept. We know that every point on the x-axis has a y coordinate of 0. That's why making y 0 leads us to the x-intercepts. So the fact that we got two solutions for x when y was 0 tells us that there are two x-intercepts, specifically -3 and 1. So I know my parabola will go through these 2 points. I don't know if it's opening up yet or opening down, but I know it goes through those 2 points. Once I find my y-intercept, then I will know which way the parabola is pointing. Because if my y-intercept is somewhere above the x-intercept here, then my parabola has to go like this. It has to open up. If my y-intercept is somewhere down here, then my parabola has to be upside down. It has to open down. So here we go, finding the y-intercept. We found y-intercepts when we were graphing lines in Unit 4. We set x equal to 0. So here's my quadratic function again. If I set x equal to 0, this term and this term will disappear, and I end up with y equals 3. So I know my y-intercept is at 0, 3. Okay. That tells me that my parabola opens up. It also tells me the vertex will be somewhere in the fourth quadrant, somewhere down here. I don't know exactly where yet. Okay, so we found the x-intercept, we found the y-intercept, and now we're ready to find the vertex. I'm going to show you two ways to find the vertex. The first way is kind of common sense. Remember I told you that a parabola is symmetrical. Okay, if it's symmetrical, that means the vertex lies on this dotted line, which runs right down the middle of that parabola. These two x-intercepts are opposite each other on the parabola. Therefore, whatever coordinates this vertex has, the x-coordinate has to be exactly halfway in between the x-coordinates of these 2 points, because this vertex is on this vertical line, which is the mirror. So if I already know the x-coordinates of these 2 points, or any pair of points on this parabola that are mirrors of each other, all I have to do is find whatever the mean is, whatever the average of these two x-coordinates is, and then I'll have the x-coordinate of the vertex. And thankfully my two x-coordinates on the x-intercepts here are very nice numbers, -3 and -1, giving me an average of -2. So I know that since -3 plus -1 over 2 equals -2, I know that my vertex has coordinates -2 comma something. Okay, well, how do I find the y-coordinate of a point if I already know the x-coordinate? I plug it into the function. So if I put a -2 into, and copy the function again, if I put a -2 in here, y will be -2 squared minus 8 plus 3. That's 4 minus 8 plus 3. And that is -1. So the coordinates of the vertex are -2, -1. So I can now graph that. It's right here. And that is enough to sketch the parabola. Okay? Every parabola you graph needs the vertex, the x-intercepts, if there are two, both of them. If there's one, the only one there is. And if there are no x-intercepts, you don't have to graph any x-intercepts. And you also need the y-intercept. And even though it's not part of the parabola per se, it's also nice to draw the axis of symmetry and write the equation of that axis of symmetry, which in this case is x equals -2. Okay, so let me summarize the process there. So first you're going to find the x-intercepts, and you make y equals 0 to find them. And that's when you choose your method, factoring, completing the square, quadratic formula. And then find the y-intercept by making x equals 0, and find the vertex. And remember, it's halfway between the x-intercepts. Now I said that the vertex has two ways of there are two ways of finding the vertex. That was the common sense way. You know it should be halfway in between, so you take the average of the two x-intercepts to find the x-coordinate of the vertex. Here's the other way, which involves a formula. Once you know this very short formula, there's much less work involved in finding the vertex. So this is finding the vertex without the x-intercepts. So if you remember the quadratic formula, this is the formula for solving for x from ax squared plus bx plus c. And these are two solutions that give you the coordinates of the x-intercepts, because there's a 0 here. So y became 0, therefore these are the coordinates of the x-intercepts. Now I'm going to write them separately, so I'm not going to use the plus or minus. Now, here's x-intercept number 1, here's x-intercept number 2. Now, if I add these two together and then divide by 2, which I just did with the numbers -3 and -1, if I add these two and divide by 2, that will be the average of these two. And that should be the x-coordinate of the vertex, right? Okay, so what happens if we add? Well, the numerator becomes this. Sorry, there should be a plus there. Plus negative b. The denominator will be 2a because both fractions had a denominator of 2a. Now what happens? I've got a positive square root of b squared minus 4ac and a minus square root of b squared minus 4ac, so those two cancel. And now I have negative b plus negative b, that's negative 2b over 2a. It turns into something very clean. I can cancel the 2's. It turns into negative b over a. But remember, I'm finding the average of these two. So I finished the adding of these two. Now I have to divide this by 2. And that gives me negative b over 2a. So this is the x-coordinate of our vertex. Quick and easy formula. If you're given ax squared plus bx plus c, the vertex will have coordinates negative b over 2a, comma, something. So let's try that with the same function we used before. This was the function. I want to know the vertex, and I don't feel like finding the x-intercepts, all right? I can do that using negative b over 2a. A is 1, b is 4. My vertex will have an x-coordinate of negative b over 2 times 1, negative 2. That's the same value we got before. And then I find my y-coordinate by plugging negative 2 into the function, which I already did a minute ago, so I know I'm going to get negative 1. Okay, so there are the two ways of finding the x-coordinate of the vertex. That's it for graphing a parabola. See you next time.